Hi, this is the complete lesson in photoelectric effect. See the description of this video. All the useful links related to my other videos are given there. Also, by using a playlist of this channel, you can navigate to any videos required. Okay, and this video, this lesson based on Edexcel IAL Unit 2 specification. Okay, so what is photoelectric effect? Means when a metal is exposed to electromagnetic radiation, it will emit electrons or it will release electrons. You know, metal consists of free electrons, delocalized electrons. So when a metal is irradiated or exposed to electromagnetic radiation, such as it could be light or ultraviolet radiation or infrared, whatever it will release electrons from it. So this process is called photoelectric effect or photoelectric emission. The electron which is released from the metal is called photoelectron. The electron which is released from the metal due to electromagnetic radiation is called photoelectron. Actually, this was first observed by Heinrich Hertz uh, in 1887. He observed this by using different apparatus, something like spark detector. He observed this photoelectric effect first time in 1887, but he couldn't explain it. But later this was explained by Albert Einstein, and he got the Nobel Prize for photoelectric effect in 1920, I think. Yeah. Okay, so in your syllabus, we normally discuss about the failure of the wave theory to explain photoelectric effect, because actually Einstein completely he proposed a completely new theory to explain the photoelectric effect, because wave theory was unable to, or even still wave theory is unable to explain the photoelectric effect. Why is it like that? That's a very generally several times that question appeared in the past paper. Why the photoelectric effect cannot be explained by using wave theory, or what is the failure of the wave theory to explain the photoelectric effect is a question appeared several times in the past papers for 3 marks or 4 marks. So first you should know what wave theory says about this observation, emission of electrons from metal. What is it saying? And we should observe, or we should compare the observation and the theory proposed based on wave theory, and then only we can explain why the wave theory is unable to explain the photoelectric effect. Okay, so according to wave theory, it says, first it says, any frequency of electromagnetic radiation must be able to remove electron or must be able to release electrons from the metal regardless of the frequency. That's the first statement or first conclusion proposed in wave theory to explain the photoelectric emission. Any frequency of electromagnetic radiation should be able to remove electron from the metal. That's the first thing, regardless of the frequency. Second, it says, if the intensity of the electromagnetic radiation is lower, the energy could be accumulated on the electrons or atoms of the metal, and the electrons could be released later with delay. That's the second proposal of second statement regarding photoelectric emission according to the classical wave theory. What it says, second thing, if the intensity of the radiation is lower, there could be delay in emission of electrons because energy has to be accumulated or build up in the matter, in the metal. So there will be delay in emission of electrons. That's the second statement or second explanation. Third one, it says, you know, electrons are released from the metal. So when the electrons are released from the metal means the photoelectrons, those are released, will have kinetic energy. So the wave theory says when we increase the intensity of the radiation falling on the metal, the kinetic energy of the electron released from the metal, that is the kinetic energy of the photoelectron, also should increase. Again I am saying, when the when the intensity of the radiation falling on the metal is increased, kinetic energy of the photoelectron also must increase. This is the third conclusion based on classical physics to explain the photoelectric effect. So I'll write all these three proposals, or all these three conclusions based on classical wave theory related to photoelectric effect. Okay, so these are the three conclusions made based on classical wave theory regarding the photoelectric effect. First, it says at any frequency of electromagnetic wave or electromagnetic radiation, electrons should be released from the metal. So the ability of removing electrons does not depend on the frequency of the electromagnetic radiation. Second, it says depending on the intensity of the radiation, there could be delay in emission of electrons from the metal, since energy has to be built up in the atoms of the metal. It says energy has to be accumulated, then the electrons could be released, because to remove electrons there should be energy required, minimum energy required. So to remove that electron, if the energy is not sufficient, it can build up, accumulate, absorbing the radiation. The energy can build up on the atoms, then the electrons could be released later after the energy of the atom becomes to the required sufficient one. That says in the second conclusion. Third one, it says when the intensity of the radiation is increased, that means you are giving more energy to the atoms of the metal, then the intensity increases. Then the kinetic energy of the photoelectron means the electron released from the metal is called photoelectron. The kinetic energy of the photoelectron also should increase. That's a third conclusion based on wave theory regarding the photoelectric effect. But what happened? Why do we say the classical wave theory is unable to explain the photoelectric effect, or it failing to explain the photoelectric effect? Because all these three observations are not tallying with the actual observations related to photoelectric effect. Actually, the first one, any frequency of electromagnetic wave of electrons should be released, it's a wrong thing, because practically what they found, experimentally they observed, for a particular type of metal, the frequency that is required has a specific lower frequency. If the frequency is lower than a specific value, the electromagnetic radiation, that particular electromagnetic radiation won't be able to release electron. That means for different types of metals, the required minimum frequency will be different. But for a particular type of metal, there is a minimum frequency to release electrons. Frequency means the frequency of the electromagnetic radiation. If the frequency of the electromagnetic radiation is lower than that specific value, that particular radiation cannot release electrons from that particular metal. That's a practical observation. These are the practical observations. But theory says any frequency of electromagnetic radiation should be able to remove electron. So the first conclusion, or first theory related to photoelectric emission based on classical wave theory is failing. First one is failing. So that's the first thing you should say, remember that. The second one, depending on the intensity of the radiation, there could be delay in emission. But actually what they found, whatever the intensity, if the frequency is above a particular value, I told that according to the first is a fail statement, but okay, you have a metal, for that particular metal, you have a sufficient frequency, above a particular frequency, you found an electromagnetic radiation. Now, if you reduce the intensity of that radiation, even when you reduce the intensity of radiation and the frequency is above the particular required minimum frequency, but there, even if you reduce the intensity, there is no delay. There is no delay in emission of electron. But what happened in here, first one, for certain metals, even if the frequency is very high, but even if the intensity is very high, those electromagnetic radiations are unable to remove electrons from certain metals, even for high intensity of radiation. But here, the second observation, they found it practically, even if the intensity is lower, and if the frequency is above a specific value, those electromagnetic radiations are able to remove electrons without any delay. So they are saying there will be a delay, that says there will be delayed emission of electron to build up the energy if the intensity is lower, but even very low intensity was able to remove electron instantaneously without any delay if the frequency of the electromagnetic radiation is above a specific value. So that is the second failure to explain the photoelectric effect by using classical wave theory. Third one, we can make an experimental setup to measure the kinetic energy of the photoelectrons. I'll explain it. I'll come to that point, how to measure the kinetic energy of the electrons released from the metal. But anyway, they were able to measure it. But it says, the third theory says, when the intensity of the radiation is increased, the kinetic energy also should increase. But what they found, when the intensity is increased for a specific frequency, imagine the frequency is above the required minimum frequency, so that frequency of radiation is able to remove electrons, okay. But when you increase the intensity, there is no change in kinetic energy of the photoelectrons. Understand? Even when you increase the intensity, if imagine an electromagnetic radiation is able to remove electron, the frequency is above a specific value for that particular metal. But when you increase the intensity, even when you increase the intensity, there is no change in the kinetic energy of the electrons released from the metal. But the wave theory says, when the intensity is increased, kinetic energy also should increase. So that also failing to explain the photoelectric effect. That means observations, what we see actually related to photoelectric effect, those all three observations cannot be explained by classical wave theory. Okay, so this is the complete explanation. Several times this question appeared in the past paper. Explain why the wave model or wave theory cannot explain the photoelectric effect, or what is the failure of the wave theory to explain the photoelectric. Either way they can ask, what's the failure of the wave theory to explain photoelectric effect, or explain why the wave model is unable to explain photoelectric effect. Either way they can ask. The answer is this one. This is the complete answer. I wrote it on the board. I already explained, so I don't need to explain again. I already explained all these three observations and the theory proposed by the wave classical wave model. So all the observations are completely disagreeing with the theory or the conclusion proposed by the wave theory. Okay, so these observations, what I explained earlier, clearly shows that the existing classical wave theory, actually that was observed during early 20th century. So during that time, quantum physics or quantum mechanics was not developed. But only thing, different scientists were proposing different ideas to develop or to build up quantum mechanics or quantum physics. Different scientists like Max Planck, Schrodinger, Heisenberg, like different scientists were proposing different ideas to develop or build up even Max Planck also part of it. So they were proposing different ideas to develop quantum physics or quantum mechanics. So during the time, scientists knew that they were unable to explain the photoelectric effect by using the existing classical wave theory, and classical wave theory is failing to explain the photoelectric effect. So what happened, Albert Einstein, he tried to explain it, but he adapted the idea already proposed by Max Planck to explain black body radiation. Actually, black body radiation, you don't need to worry. That is in little bit, we will learn that in unit 5 under cosmology. Black body means that emits almost all the radiation. Even black body does not mean it's black color. Even sun, stars, they are treated as black bodies. Anyway, you don't need that. But Max Planck, he proposed an idea about the radiation given out by a black body. Black body gives out infrared or gives out electromagnetic radiation. So Max Planck proposed that the energy of the electromagnetic radiation is not continuous. Actually, according to classical wave theory, energy is continuous. But he proposed, Max Planck, in his black body radiation, that theory, uh, the energy of electromagnetic radiation is not continuous, it is discrete packets of energy. It's difficult to imagine, but theoretically he proposed it. That means the energy of electromagnetic radiation could be treated as discrete packets of energy, and one particular packet of energy is proportional to frequency of the electromagnetic radiation. So he said the smallest packet of energy of electromagnetic radiation is directly proportional to its frequency. So there must be a constant, when we change the proportionality into an equation, there will be a constant. That constant is called Planck constant later, because Max Planck proposed this idea. So to respect him, his name was given. So we can say the energy of the discrete packet of smallest discrete packet of energy is equal to E equal h times f, where f is the frequency of the electromagnetic radiation, h is a constant called Planck constant. It's called Planck constant, and E is the energy of the electromagnetic, E is the energy of the photon. We call the smallest discrete packet of energy is called photon. So what he proposed, the electromagnetic radiation could be treated as, it consists of several discrete smallest packets of energy. Each packet of energy is proportional to frequency of the electromagnetic radiation, which is given by E equal hf, where f is the frequency, this is a Planck constant, and E is the energy of the packet of energy. This is called the discrete packet of energy is called photon. Discrete packet of energy is called photon. So h is called Planck constant. So h has a value 6.63 10 to the power minus 34 joule second. So E is the energy of a photon. So what is photon means? Discrete packet, smallest discrete packet of energy of electromagnetic radiation. Smallest discrete packet of energy. The word discrete must be there. Discrete packet of energy of electromagnetic radiation is called photon. Okay, so according to the theory proposed by Max Planck to explain the black body radiation, energy of the photon is discrete, not continuous. We call it is quantized. The energy of the photon is quantized because it can have only certain amount of energy depending on the frequency. But according to classical wave theory, a wave can have any amount of continuous range of energy, any amount of energy. It's not discrete. According to classical wave theory, the energy of the wave is not discrete, it is continuous, a range of spectrum. But according to Photon model, we call Photon model is the model proposed by Max Planck, in which he proposed the energy of the photon, discrete packet of energy. So according to that, the energy of the electromagnetic radiation is carried by discrete packets of energy called photons. The energy of the photons are quantized. Quantized means they can't have continuous value, only certain values they can have depending on the frequency. uh, Analogy. Sometimes students ask what's the meaning of quantized and what's the meaning of continuous, or what's the meaning of continuous and discrete. Imagine something like there is analogy, nothing related to photoelectric, don't get confused, but just an analogy. Imagine there are two, a building has two floors. You want to climb from this first floor to the second floor along a slope. So you can stand at any point on the slope. That is called continuous. You can have any gravitational potential energy when you climb from ground floor to the first floor. You can stand at any point because the slope is continuous. But imagine if another person is climbing on a step. There's a staircase that has certain number of steps needs. There he can't have any amount of energy, so he has to stand in one of the steps. Either he has to be here on this step or next step. He can't stand somewhere between these two steps. That means he can't have gaining gravitational potential energy continuous. It's discrete. Either this amount related to this height or this amount of GPE depending on this height. He can't fly or he can't float somewhere between this height and this height. So here the gain in gravitational potential energy when he climbs from the ground floor to first floor are discrete, quantized gravitational potential energy he can gain when he climbs from ground floor to first floor. But here when he walk on a slope, he can have any amount of continuous, any amount of gaining gravitational potential energy when he walks from ground floor to first floor. Here the gaining gravitational potential energy is discrete or quantized. Only certain amount of GP he can gain. Anyway, nothing related to photoelectric effect, nothing related to quantum physics, but analogy to make you to understand the difference between continuous and quantized. I use this example. Okay, so we know that Albert Einstein adapted Max Planck's idea regarding photons. Now he is using it to explain the photoelectric effect. So when he explains, he stated first he proposed a postulate. Postulate means it's not an assumption. It's like assumption, but no reason. It's a basic fundamental assumption we can take, a postulate. So what he postulates, he said one photon can interact with only one electron. It cannot share its energy with more than one electron. He proposed that one photon can interact with only one electron. It cannot share its energy with more than one electron. Also he said, when it interacts with an electron, that means when it meets an electron, either it will give all its energy to the electron or it won't give any energy to the electron. That means it can interact with only one electron. Also, when it interacts with the electron, photon never shares its energy. Shares its energy means, for example, a photon is carrying, normally we use notation for photon like this. A photon is carrying, for example, 10 joules of energy. To remove an electron from the atomic bond, you know, the nucleus keep the electron together due to the electrostatic attractive force. Imagine to remove the electron from the atom, the required minimum energy to remove the electron, for example, if it is 4 joule, it's not like that. The photon gives 4 joule to remove the electron and the photon carries the balance energy of 6 joule. No, it never shares its energy with the matter means electron. Either it will give all its energy to the electron, or it will move without any interaction. So you know that if it share all its energy, or if it gives all its 10 joules to the electron, the energy required to break the electron is 4 joules. So there is 6 joules already given to it. That will be the kinetic energy. The electron will be knocked out with that kinetic energy. That's the idea he proposed. So first you should know the postulate: one photon can interact with only one electron. Second, he said when a photon interacts with electron, it never shares its energy. Either it will give all its energy to the electron, or it won't give any energy to the electron. Third one, he said the photon behaves like a particle. That means when it meets or interact with the electron, without any delay, it will knock out the electron. That means, you know, the classical physics, they said energy can be absorbed and built up. So here he says, photon behaves like a particle. When you throw a marble, there's a marble kept on a table, and you are throwing another marble to it. So the marble won't be won't be in contact with this marble for 5 seconds, then knock out. No, when it hits, it will knock out, is it? Particle, they behave like that. So he said the photon behaves like a particle. When it interacts with the electron, immediately without any delay it will knock out the electron. So, and then he says the fourth one he proposes in theory: ability of removing electron from metal does not depend on the energy of the whole wave. It depends only on the energy of each and every individual photons. Careful, again I am saying, he said the ability of removing electron does not depend in the complete energy of the wave. It depends only in each energy of each and every photon. That's the way he proposed. So that means if to remove an electron from a metal, the energy of the photon should be sufficient to knock out the electron. Not many electrons, many photons come and hit one after other, and they can remove the electron. Never happens. One photon interacts with one electron, and ability of removing an electron depends completely on the energy of the photon. It does not depend in the energy of the whole wave. Okay, so these are the very important final things regarding Albert Einstein's proposal to explain the photoelectric effect in his theory. First he said, I already told, again I am telling, one photon interacts with only one electron. I already explained that. A photon, either a photon will transfer all its energy to an electron, or the photon will not transfer any energy to an electron. That means we normally say, in a normal way we say photon can't share the energy. Share means give some energy, a few amount of energy to the electron and move with the balance energy. That never happens. The third one, ability of removing an electron completely depends on the energy of a photon and not depends in the intensity of the wave. So it depends on energy of each and every photon, not depend on the intensity or the whole energy of the wave. Individual photons should decide whether they are able to remove the electron or not. Fourth one, photon behaves like a particle, he said, because he said the photons won't take time to have contact and release the electron later. No, they behave like a particle. When they hit the electron will be knocked out without any delay. So based on this, he developed his theory. Actually, it's full of mathematics, but we don't teach any of them. But in a simple way, very simple way, we give the equation related to Einstein's photoelectric equation. We say that it's a very simple way we give it. Looks like very simple, anyone can do, but actually the theory he proposed depends on a lot of mathematics, but we won't go into that detail. So now I'll give the equation given by or proposed by Albert Einstein to explain the photoelectric effect. Simple equation based on these proposals. Okay, so when we consider a metal, it consists of delocalized electrons, free electrons. These free electrons exist in all part of the metal. So if I draw an enlarged diagram like a metal block, but actually I'm drawing a metal plate. Okay, so there will be delocalized electron everywhere on the in the metal. It could exist inside the metal as well as on the surface of the metal. Everywhere there will be delocalized electrons. Experimentally, we can show that for a particular type of metal, say for example sodium, or for a particular type of metal, something like cesium, right? The minimum amount of energy required to remove an electron from the surface of metal is constant for a particular type of metal. The minimum amount of energy required to remove an electron from the surface of metal is constant or fixed for a particular type of metal. But when we consider the same metal, the minimum amount of energy required to remove an electron from interior part or inner part of the metal could be different depending on the points or positions we consider, because depending on the atomic plate structure, why we need minimum amount of energy to remove an electron? Because when you consider an electron on the surface of the metal, that electron is bound or attracted by its own nucleus. Also, other nuclei can exert electrostatic force on the electrons. To overcome and remove the electron, we need a minimum amount of energy to overcome the attractive force by the nuclei. But when we consider inner electrons, the minimum amount of energy required could be different, because that electron could be attracted by different nuclei surrounding it, and it cannot have a constant value, because it could be different depending on the positions and depending on the location inside the metal. So normally we consider only the surface electrons. For a particular type of metal, the minimum amount of energy required to remove an electron from its surface is constant, and that minimum amount of energy to remove an electron from the surface of metal is called work function of the metal. It is called work function of the metal, and it is denoted by a notation phi. So the word work function is applicable only for the surface electrons, not inner electrons, because inner electrons might have different energy to remove them, because they could be attracted by many nuclei surrounding it. So we don't consider the inner electrons when we talk about photoelectric effect. We consider only the surface electrons. For surface electrons, it is constant for a particular type of metal, which is called work function. So in the exam they ask, what define work function, or what is work function? Minimum amount of energy required to remove an electron from the surface of metal is called work function. Okay, but when we consider different types of metals, say for example copper, and the next type of metal could be cesium, or maybe sodium, whatever it is, cesium or sodium, whatever it is. For them the work function will be different, because different type of metals have different atomic arrangements, and their structure of the nucleus is different. So therefore different types of metals will have different work function. For a particular type of metal, work function is constant. The word work function is applicable only for surface electrons. Inner electrons, for a particular type of metal, the required minimum energy could be different at different points inside the metal. Okay, so work function is the property of the type of metal. Now next thing is threshold frequency. We know minimum amount of energy required to remove an electron from the surface of metal is called work function. So that means the electrons are going to be removed by electromagnetic radiation. We know electromagnetic radiation, energy of the electromagnetic radiations are carried by discrete packets of energy called photons. So minimum amount of energy required to remove an electron from the surface of metal is work function. So the minimum amount of frequency of electromagnetic radiation to remove an electron from the surface of metal is called threshold frequency of the metal. That means minimum amount of frequency of electromagnetic radiation to remove an electron from the surface of metal is called threshold frequency. It is denoted by F naught. So the F naught and the work function are related by minimum amount of energy required to remove an electron from the surface of metal is called work function. So that minimum amount of energy should be carried by a photon, because according to Einstein's proposal, one photon can remove only one electron, and one photon, each and every photon should have the sufficient energy to remove the electron. So if a photon wants to remove an electron from the surface of metal, the photon should carry an energy at least equal to work function. So the energy of the photon, minimum amount of energy required to remove an electron is called HF naught, where F naught is the threshold frequency of the metal. That is the minimum frequency of required to minimum frequency of the electromagnetic radiation to remove an electron from the surface of metal. So phi equal HF naught, but we know that C is equal to V equal F lambda. C is equal to F naught lambda naught, where lambda naught is called threshold wavelength. So we can write phi is equal to H. Instead of F naught, I can write F naught is equal to C over lambda naught. So phi equal HC over lambda naught, where lambda naught is called threshold wavelength. So threshold wavelength is defined as maximum wavelength. So if I make the lambda naught subject, lambda naught is equal to C over F naught. So we see minimum frequency of electromagnetic radiation to remove an electron from the surface of metal is threshold frequency. C is constant. When F naught becomes the minimum required frequency, when you divide, it's in the denominator. So F naught becomes minimum, lambda naught will become maximum. So how do we define the threshold wavelength? Maximum wavelength of an electromagnetic radiation, maximum wavelength of an electromagnetic radiation to remove an electron from surface of metal is defined as threshold wavelength of the metal. It's a property of the metal, but the frequency or wavelength required from the electromagnetic radiation. So threshold wavelength is defined as the maximum wavelength of electromagnetic radiation to remove an electron from surface of metal. Okay, so we already learned, I uploaded the video related to intensity, but in photon model, how do you define intensity? The definition is the same. Intensity is the amount of energy or amount of power passing through unit area. Amount of power of the electromagnetic radiation or passing through unit area is defined as I equal P over A. We already learned that. That is the intensity. But when we consider electromagnetic radiation in photon model, Max Planck proposed that energy is carried by photons. Energy of electromagnetic radiation is carried by photons. So when we consider the intensity, here the definition is the same. Amount of energy passing through unit area per second, or amount of power passing through unit area is the intensity. But the energy is carried by the photons. So there we can say the intensity as each and every, for a particular frequency of electromagnetic radiation, each and every photon will have the same energy, that is equal to E equal HF. So through unit area per second, the number of photons passing through, if I take n, then the total amount of power passing through unit area per second is given by n times HF. HF is the energy of a photon, where n is the number of photons passing through unit area per second. So n into HF gives the amount of energy passing through unit area per second, that is the intensity. So in photon model, intensity is given by I equal n times HF, where HF is the energy of the photon, energy of a photon of particular frequency of electromagnetic radiation. What is n? N is the number of photons passing through unit area per second. But this is not a standard equation, but you can use it. But when you are using it, you have to define what is n. N is the number of photons passing through unit area per second. Then this is the total amount of energy passing through unit area per second, because energy is carried by the photons. So this is the equation for intensity in terms of energy of photon and number of photons passing through unit area per second when we consider the photon model. Okay, so now we are going to get the final equation proposed by Albert Einstein related to photoelectric effect. This looks very simple, but actually the way he proposed and derived are different, full of mathematics. But those are not in your syllabus. One thing you should know, work function is the minimum amount of energy required to remove an electron from surface of metal. We don't talk about work function for inner electrons, or the minimum amount of energy required to remove an electron from inner part of the metal could be different at different points, so we don't consider. Also, Albert Einstein, he proposed in his theory that one photon can interact with only one electron. Either it will give all its energy to the electron, or it won't give any energy to the electron. So by using that, we can simply get the final equation for the photoelectric effect. Say for example, this is the metal. So we consider the surface electron, because work function we are going to consider. We can't use the word work function for inner part of the metal. So there's a photon. So the photon we denote by this way. So there's a photon, its energy E is equal to HF. F is the frequency of the radiation. This is one photon, one photon. So there's a electron on the surface of metal. So the minimum amount of energy required to remove an electron from the surface of metal is the work function phi. So to remove the electron, the energy of the photon HF must be greater than or equal to work function. If it is greater than the work function, the photon has balanced energy, but it won't share it with the electron. That means it won't share means the photon can't continue its motion with the balanced energy, because photon will either give all its energy or it won't give any energy. So the photon has balanced energy if HF is greater than work function. The reminder, the balanced energy of the photon will be given to the electron as kinetic energy. So when I relate all these three different types of energy, like a conservation of energy, but actually that is not the case, but we are going to derive like that simple way. Energy of the photon is HF. The photon will give all its energy or it won't give energy. If it gives all its energy, the energy of the photon is given to remove the electron, just to break the bond from the atomic nuclear attractive force. It has to do work against the attractive force, that is the work function. Work function, and the balanced energy will be given as the kinetic energy. When you expose a metal, now we'll think little practical. When we expose or irradiate a metal with a particular frequency of electromagnetic radiation, HF, there are many delocalized electrons on the surface, inner part, everywhere. There will be different delocalized electrons. So imagine many different photons are falling on the metal. Certain photons might remove electrons from the surface of metal. Certain photons might go deeper and remove electrons from the inner part of the metal. But wherever a photon removes an electron, it will give all its energy to the electron or it won't give any energy. That principle will be followed anywhere, whether it's removing an electron from the surface or inner part. Okay, we'll consider inner portion. So inside an electron, the energy required to remove or break the bond, I told that will be greater compared to the surface electron, because inner electron might have attractive force by many nucleus surrounding it. Let that energy be phi 1. So energy of the photon is same as HF. There also it will share it. Phi 1 is the minimum energy required to remove an electron from the inner part of the metal. Anyway, phi 1 will be greater than phi. Phi is the work function for the surface electron. The balance will be given as kinetic energy. So it could be different for different part of the inner electrons. To remove electron, the work functions could be different. And the electrons, when they come out, when they are removed, and when the electrons move from the inner part, those electrons also might have collision with other electrons, so they might lose their kinetic energy, or the kinetic energy will decrease. Therefore, when you have a practical and measure the kinetic energy of the electrons, you will see there will be several electrons released from different part of the metal. They all will have different magnitude of kinetic energy depending on the position from where they are removed. But only the surface electron will have the maximum kinetic energy, because two reasons. The surface electron has the minimum amount of energy required to remove it from the attractive force of the nucleus. The second reason, the minimum, the electron which is removed from the surface has no chance of hitting any other electron. But inner electrons, when they are released, when they approach to come out of the surface, they might have several collisions even inside the metal, so they might lose kinetic energy. So the surface electrons will be released with the maximum kinetic energy. But experimentally, when you measure the kinetic energy of the electrons released during photoelectric effect, or during a metal is exposed to electromagnetic radiation, you will see there will be different kinetic energies of electrons will be released from the metal, but they will have different kinetic energies depending on the position. But only the surface electron will have the highest or maximum kinetic energy. And the photoelectric equation proposed by Albert Einstein, we use only for the surface electron. That's the reason we put this as Ke max, because this is applicable only for surface electrons. The surface electrons will have the maximum kinetic energy. So we can write this HF equal phi plus half m v max square. That way also some books they write m is the mass of the electron released from the metal, that v max is the maximum speed of the electron that belongs to the surface. Instead of f we can write c over lambda, so we can write h c over lambda, nothing new. V equal f lambdas, f equal c over lambda equal phi, that's the work function, belongs to the surface of the metal, half m v max squared, maximum speed belongs to the surface electron. So we don't use this equation for inner electrons, I already explained several times. We use this equation only for the surface electrons. So this is the final equation proposed by Albert Einstein to explain the photoelectric effect. Okay, so how does photon model of electromagnetic wave explain the photoelectric effect, or how does particle nature of light or particle model of light, several ways they ask, explain the wave photoelectric effect? Okay, we learned that already, I discussed what are the failure of wave model or classical wave theory to explain the photoelectric effect. First failure, wave theory is unable to explain. Wave theory says any frequency of radiation can remove electrons from metal regardless of the frequency. Any frequency should be able to remove electron, but practically they found to remove an electron the frequency should be above a particular value. How it is explained by this model? Okay, we know that in Albert Einstein's photoelectric effect theory, he proposed that ability of removing electron completely depends on energy of each and every photon and not depend on the intensity of the wave. He said ability of removing electron completely depends on, or totally depends on, energy of each and every photon and not depend on the intensity of the wave, he said. So if we use that statement, we know that to remove an electron, we need at least a minimum energy to overcome the attractive electrostatic attractive force by the nucleus. So that means if the minimum amount of energy required to remove an electron from the surface of metal is the work function L phi, that is given by hf naught. We know that work function is given by hf naught in terms of photon model. And we know that to remove the electron, energy of the photon, a photon is hitting or falling on the surface of metal. The energy of the photon E is given by HF. To remove the uh, electron, the energy of each and every photon must be greater than work function. According to photon model, energy of each and every photon must be greater than or equal to work function of the metal. So HF is greater than or equal to, instead of phi I can write HF naught to remove the electron. That means the frequency of the radiation must be H and H get cancelled. Frequency of the radiation must be greater than equal to a particular minimum frequency, that is called threshold frequency. See, it explains the photoelectric effect. Wave theory says any frequency must be able to remove electron because there they consider the whole intensity of the wave. But here Albert Einstein, he proposed it does not depend, the ability of removing electron does not depend on the whole energy or the intensity of the radiation. It depends only on the energy of each and every photon. So energy of each and every photon, HF, must be greater than the required minimum energy to remove electron from the surface. So HF must be greater than HF naught, means the frequency of the radiation must be greater than threshold frequency. Each and every metal has a threshold frequency. So if the frequency is greater than the threshold frequency only, the electron will be removed. So first problem what we had, that means we were unable to explain by wave theory. Now we are able to explain it by using the photon model, the first complication or first problem. Okay, the second problem or complication we had in wave theory says if the energy, depending on the intensity, there could be delay in emission of electrons because energy has to build up. But here Albert Einstein, he proposed photon as a particle. Problem solved. He said photon behaves like a particle. So one photon knocks out one electron without any delay. So it happens practically. So the practical observation is explained by using photon model because photons behave like a particle. Second problem also solved. The third problem, what the wave theory says, when the intensity of the electromagnetic wave increases, kinetic energy of the electrons removed also should increase. Now we will see how the photon model is solving this problem. We know that intensity of electromagnetic radiation in photon model is given by I equal n times hf, where n is the number of photons passing through unit area per second. HF is the energy of a photon. I can put in a bracket if I want. HF is the energy of photon. Say for example, you are having a bulb, monochromatic bulb. Imagine a green color bulb connected to a battery, simple circuit I'm doing, connected to a power supply, and there is a variable resistor. Okay, you are changing the variable resistor, you are reducing the variable resistance of the variable resistor. So the monochromatic bulb means frequency of the radiation emitted is constant. So when you are reducing the resistance, current flow will increase, so power dissipated or emitted from the bulb will increase, so intensity, brightness of the light will increase. So what happens in terms of photon model when the brightness or the intensity of the light is increased? Here there is no change in frequency of each and every photon. We are going to explain that in terms of photon model. The each and every photons emitted, there is no change in the energy of each and every photon because it's still the same green color light it's emitting. Only thing, the brightness is increasing, means the bulb will throw away, the bulb will emit more number of photons per unit area per second. That means when you are increasing the brightness of the bulb, n will increase. By keeping the frequency of the light constant, the monochromatic light, when you increase the brightness of the bulb or brightness of the light, what happens? No change in HF, but n will increase. What is n? Number of photons emitted by the bulb per unit area per second will increase, n will increase. Remember that happens according to photon model. Okay, so here in the wave theory we had a problem. Wave theory says when the intensity of the wave increases, kinetic energy of the electron released must increase. But we know the equation for kinetic energy of the electron according to Einstein's equation, HF equal phi plus Ke max for the surface electron. For inner electrons, we can't put Ke max, Ke, here phi 1 or something we can put. Okay, now intensity is given by I equal n times HF. Right, now problem solved according to photon model. Wave theory had a problem. Wave theory says when the intensity increases, kinetic energy should increase. Now look at here. But practically they observe no change in kinetic energy. See, I'll explain. Here I can explain there is no change in kinetic energy when the intensity increases. Now when you increase the intensity, I already explained by using the green color bulb. When you increase the intensity by keeping the frequency constant for a monochromatic light, frequency constant, when you increase the intensity, n will increase. Number of photons falling on the metal per unit area per second will increase. But here in this equation there is no change because you are not changing the frequency. So HF is not changing. Work function is constant for a particular type of metal. So even when you increase the intensity, there is no change in this equation. Nothing is changing. So kinetic energy will remain constant. So that problem also solved by using photon model. Okay, so next topic is measuring the kinetic energy of fastest electron. Okay, before that we should know what is photovoltaic cell or solar cell. Actually, we know everything now. We are finishing the topic. We know the electrons will be released from the metal, and if we have a complete circuit, there will be current flow. Say, for example, we can have a set. We can buy the photovoltaic cell or the solar panels. Imagine this consists of emitting electrode. Here there is an emitting electrode, and there is a collecting electrode, and there should be a hole with a glass or something like this. There's a lens or whatever it is. So this is the emitting electrode. So the radiate inside it's vacuum. There's nothing inside. This is vacuum. Avoid unwanted collision with air particles. And if the radiation falls on the emitting electrode through the lens, if the radiation falls on the emitting electrode, the electrons will be knocked out and the electrons will flow towards the collecting electrode. So the electrons will move towards the collecting electrode. And if we complete a circuit like this, if we have a complete circuit like this, we can have a flow of electrons, or we can have a diode or whatever. The electrons will be collected by the collecting electrode. So this is losing the electrons because the electrons are knocked out by the photon. So this will become losing the electrons, so it will become positive. So inside there will be electric field. So the electrons will be collected by the collecting electrode and the electrons will flow in this direction. So there will be current flow opposite to the direction of flow of electrons, that is called photocurrent. Current flow due to photoelectrons is called photocurrent. Inside it is vacuum. So the electrons are released, and the electrons those are released due to photoelectric effect will move from emitting electrode to collecting electrode, and they will complete the circuit. So the current will be in opposite direction. Okay, so here one thing we should know. So inside a photo cell, it's vacuum and the electrons are released from the emitting electrode and collected by the collecting electrode. But if you have same thing like inside not a photovoltaic cell, something like students have confusion. If you have two metal plates, not a photo cell, just two metal plates, it's vacuum inside. If I connect a battery externally, something like if I connect a battery like this, students ask, will there be current flow? No, the current flow won't be there because now this positive terminal make this uh, terminal positive. This will create this as negative. There could be electric field inside, but electrons won't jump from this plate to this plate because it's vacuum. Electrons can't pass through the vacuum unless you apply very high voltage, something like 2500 volts, something like that. Then it can break the insulation and it can have spark inside, something like lighting. But otherwise, if it's for a normal DC power supply, something like even for 2450 volt, there won't be any current flow, there won't be any flow of electrons inside the completed inside, even if it is vacuum, there won't be any flow of electrons. But when we have photo cell, if it is a photo cell or photovoltaic cell or solar panel, there the electrons are really removed from the photons, and those electrons are flowing from emitting electrode to collecting electrode. So remember that the external power supply can't create current flow between two terminals. Those are kept far apart. Inside a vacuum, there can't be any current flow. But the current flow here due to the electrons released by the photoelectric effect. Okay, so how do we measure the kinetic energy of the fastest electron? We should use a photovoltaic cell, something like this. So there must be emitting electrode and there's a collecting electrode. So through the lens, electromagnetic radiation should be allowed to fall on it. We can use different color lights with known frequency, and here there should be a circuit. Here we can have a microammeter or picoammeter because current flow is very low. We can have a picoammeter to measure the current flow. So if we have a complete circuit, there will be current flow. But what we are going to do, here our aim is to measure the kinetic energy of the fastest electron. So to measure the kinetic energy of the fastest electron, we should have a circuit, something like we should be able to stop the flow of electron. So what we are going to do, we are going to have a opposing voltage by using a variable power supply. Some books, instead of this one, they put a potentiometer, but I just directly use a variable power supply. So this is the positive terminal, this is the emitting electrode, this is the collecting electrode. So the electrons are emitted from the emitting electrode and they are moving towards the collective electrode. Those are the photoelectrons. These electrons flow in the circuit and cause the photocurrent. Now what we are going to do for a particular frequency of electromagnetic radiation, for a particular frequency, imagine I am using a red color light. I know the frequency of the light also, if I do that way. Now first you keep the voltage, the variable power supply 0, then there will be current flow. But increase the voltage gradually. When you increase we call this as an opposing voltage. When we increase the voltage, what will happen? This will develop an electric field inside the in between the emitting electrode and the collecting electrode. It will develop an electric field. So the or simply we can say this positive terminal will make this as positive, this negative terminal will convert this collecting electrode into negative. So the electrons, those are moving emitted from the emitting electrode. When they move from emitting electrode to collecting electrode, these electrons will be attracted by the positive terminal because this opposing voltage, what we are using externally, this is positive terminal that will try to attract the electrons, and also this negative terminal will push the electrons. So the electrons, those are moving from emitting electrode to collecting electrode, will experience opposing force. They have to do work against opposing force. So when they move from, when they are released from the emitting electrode, they had kinetic energy. But when they move towards the collecting electrode, they are going to lose their kinetic energy because of opposing force created by the electric field by this external power supply. And there should be a voltmeter connected here. There must be a voltmeter also. So what happens? The electrons, when they are moving from emitting electrode to collecting electrode, they are going to lose their kinetic energy. Something like if I throw a pen vertically upwards, when it leaves my hand, the pen has kinetic energy, but when it moves upwards, it experiences opposing force due to gravitational pull. So the pen will lose its kinetic energy. So there I can say loss in kinetic energy equal gain in gravitational potential energy. Here, when the electrons move from here to here, loss in kinetic energy is equal to gain in electrical potential energy. Electrical potential energy is given by W equal QV. Q is the charge of the electron, or W equal QV. V is the potential we are applying externally by using this power supply. Q is the charge of the electron. So when the electrons are moving, they'll experience opposing force, they lose their kinetic energy. So what happens when you are doing practical? This practical should be started with very low voltage, almost equal to zero. That time there will be current flow, so the picometer will read a maximum value. When we increase the opposing voltage gradually, what happens? I told when a metal is exposed to electromagnetic radiation, electrons will be released with range of kinetic energy. Surface electrons will have the maximum kinetic energy. Inner electrons will have lower kinetic energy. I already explained those. So the electrons with lower kinetic energy could be stopped easily by using less amount of work done against their motion. So when you increase the opposing voltage from zero, what happens? The electrons, those emitted with lower kinetic energy, will be stopped first. Then gradually other electrons also will be stopped when you increase the voltage. So the rate of flow of electrons will decrease because the electrons are losing their kinetic energy. They are unable to reach the collecting electrode, so there will be less amount of rate of flow of photoelectrons, less amount of photocurrent. So the current flow will decrease gradually. So the current flow is equal to rate of flow of photoelectrons. So when there are lot of rate of flow of when there are larger number of photoelectrons, rate of flow of photoelectrons higher, photocurrent will be higher. Photocurrent is the current created by photoelectrons. When there are less amount of photoelectrons, what happens? Rate of flow of photoelectrons will decrease, photocurrent will decrease. So when increasing the opposing voltage, gradually electrons are losing their kinetic energy. So the number of electrons collected by the collecting electrode per second will decrease. Rate of flow of photoelectrons will decrease. Picometer reading will decrease. So you increase it gradually and slowly and carefully. At a particular voltage, what happens? The picometer reading will become zero. That's very important. The picometer reading becomes zero means you have stopped all the photoelectrons emitted from the emitting electrode, and none of them are reaching the collecting electrode, because even the fastest electron which is emitted from the surface is stopped. Okay, even when the picometer readings become zero, that means all the photoelectrons, including the fastest electron, is stopped. So when the fastest electron is stopped, there we can write loss in kinetic energy, loss in kinetic energy of the fastest electron equal to gain in electrical potential energy. Electrical potential energy by the electron. Okay, loss in kinetic energy of the fastest electron is Ke max. It lost all the energy. That's the reason it's unable to reach the collecting electrode. So Ke max is equal to gain in electrical potential energy. I told gradually and carefully increase the opposing voltage. When the picometer becomes zero, immediately stop increasing further beyond it. So that time, record the voltmeter reading, that let it be Vs. When the picometer reading becomes zero, at that moment the voltmeter reading is Vs. So I can say this is equal to QVs. Q is the charge of the electron, or some books they use EVs. E is the charge of electron. Either way, Q or E you can use, no problem. Where Q is the charge of electron, Vs is the voltage recorded by you when the picometer reading becomes zero. Now we know that Vs is recorded from the voltmeter. You know the charge of electron 1.6 10 to the minus 19. We know the kinetic energy of the fastest electron. Now I can say HF equal 5 plus Ke max we use for the surface electron. HF equal 5 plus, instead of Ke max I can write QVS because we are measuring the Ke max by using this method where Vs is the stopping potential. So here we know that H is constant, Planck constant for a given emitting electrode, that is for this metal, this is the emitting electrode, phi is constant, Q is constant, charge of the electron. So only possible variables are frequency of the radiation. I can use different color lights with known frequency and I can record the relevant stopping potential. This is the independent variable, this is the dependent variable. Make the Vs subject. So I can repeat this experiment for the same photovoltaic cell. The work function of the emitting electrode is constant. Repeat the same experiment for different frequency of known color lights. So, and record the corresponding or relevant stopping potential. So make the Vs subject. Vs is equal to H over Q times F minus phi over Q. Carefully see the rearrangement. Vs is the dependent variable, F is the frequency, independent variable. So Vs equal H over Q into F minus phi over Q. So this is on the y-axis, y equal. H is a constant, Q is a constant, so that could be a constant, so that could be the gradient. Frequency is the independent variable x-axis. Phi and Q are constants for a given metal, so they could be the y-intercept point. So if you plot a graph, you will get a graph like this. Y-axis, stopping potential, x-axis, frequency. Then the graph will be a straight line where the graph cuts the x-axis, where the graph intercepts the x-axis, that will be equal to threshold frequency. How do I know that is equal to threshold frequency? You know at this point Vs equal to 0, the Vs equal to 0, substitute Vs equal to 0 and see what could be the value. If I substitute Vs equal to 0 in this equation, 0 is equal to H over Q F minus phi over Q. Multiply the whole equation by Q, so you'll get HF minus phi equal to 0. So we know phi is the work function which is given by HF naught. So I can write HF minus HF naught equals 0. So F equal F naught when Vs equal to 0. Very important conclusion. That means the graph where it cuts the frequency axis gives the threshold frequency. Remember that where it cuts the x-axis gives the threshold frequency. So lower than threshold frequency, practically you can't get a value. So we can just extrapolate, but it can be a graph. So we extrapolate where it cuts the y-axis, that will be minus work function over Q. Remember these quantities and you must be able to rearrange this and get the relevant equation. So remember that where the graph cuts the x-axis threshold frequency, where it cuts the y-axis is minus work function over Q. Q is the charge of electron. And there you can't draw a solid line because there is no data below threshold frequency. There won't be any emission of electrons. So only thing you can extrapolate, and you can intersect the extrapolate line to the y-axis. If you find the gradient, so after plotting this graph, if you find the gradient of the graph, remember all these things, gradient give H over Q. So the gradient M is equal to H over Q. So if you know the gradient, if you know the Q, you can find the Planck constant as gradient times charge of the electron. There could be questions based on these also. Remember what quantities are used as y-axis and x-axis, which quantities could be found by using the graph where it cuts the x-axis threshold frequency, where it cuts the y-axis phi over Q, gradient gives H over Q. Remember that. Here I am plotting a graph of stopping potential against frequency for different frequency of electromagnetic radiation, different known frequency. Similarly, Sometimes they give a graph slightly different. So here I plot a graph of stopping potential against frequency. I can erase it. I don't need this setup anymore. So I can plot a graph of, here I plot the graph of stopping potential against frequency. Sometimes the question papers, they give a graph of kinetic and maximum kinetic energy against frequency. Nothing, that's much easier. So they use the equation directly, this one, HF equal, that is HF equal phi plus Ke max. They calculate the Ke, so practically they measure the Vs, multiply by the Q, and they calculate the Ke max, and Ke max is taken as the y-axis. So Ke max is taken as the y-axis. So here phi is constant, h is constant. For different f, there could be different Ke max. So Ke max is the dependent variable, frequency of the electromagnetic radiation is the independent variable. So I can make the K max y-axis. K max is equal to HF minus phi. So this is y-axis equal, h is a constant, m, frequency is independent variable minus c. So here if you plot a graph of K max, maximum kinetic energy against frequency, here also you will get the same shape of graph. That's going to be y equal mx minus c. So here also where it cuts the x-axis is the threshold frequency. Extrapolate, where it cuts the y-axis is the work function directly. The gradient gives, here the gradient gives h. Careful, the difference between two graphs. Here stopping potential against frequency. Here kinetic energy, maximum kinetic energy of the electron, that is surface electron or fastest electrons, kinetic energy against frequency. The properties are different. Gradient gives h here. Y-intercept point gives the work function. X-intercept point gives the threshold frequency. Here also x-intercept point is the threshold frequency, but the y-intercept point is phi over q, gradient h over q. Remember these things. There could be questions. Okay, so if you do different photovoltaic cells you are using different photovoltaic cells. One photovoltaic cell consists of cesium as the emitting electrode, so I drew and erased it. Yeah, you are using different photovoltaic cells. One photovoltaic cell in which the emitting electrode is cesium, and you are doing a practical and you got the graph. Then you are using separate another type of photovoltaic cell. It consists of different type of metals, and if you do the practicals with three different types of photovoltaic cell and you are plotting the graph on the same axis, what type of graph will you get? You can see that here the cell that has the lowest threshold. Now the graph all will be parallel because all the graphs will be parallel to each other. If you do the same experiment with different photovoltaic cells, those have different metals as the emitting electrodes. There, you know the y-axis you are keeping. If I consider this graph, stopping potential against frequency for three different types of photovoltaic cells. You have done the practical. You got three different graphs. This is Vs. Okay, so all three graphs will be parallel to each other. Why are they parallel? You can see the gradient for all three graphs. Only thing different photovoltaic cells means they will have different work function. That's all. That's the only difference. Different work functions. They will have different work functions. Okay, but otherwise, different work functions mean phi equal HF naught, different threshold frequencies. Different work functions, so different threshold frequencies. But all the practicals will have the same gradient h over q. H is constant, q is constant. So you will get three different photovoltaic cells. If you have used, you will get three different parallel lines. First line, second line with the second photovoltaic cell, and the third line with the third photovoltaic cell. All graphs will be parallel to each other. The reason, if they ask why are they parallel, rearrange the equation and show for all the photovoltaic cells, they have different work functions, so different threshold frequency, but they have the same gradient. H is constant, Q is constant. Same gradient means they will have the same parallel, they will be parallel to each other. But the photovoltaic cell that has the lowest threshold frequency, the photovoltaic cell that has the lowest threshold frequency will be closer to the y-axis. This may be the lowest threshold frequency. If not, this is the next highest threshold frequency. This is the maximum threshold frequency. So the lowest threshold, the emitting electrode with the lowest threshold frequency will be closer to the origin. That will have the lowest threshold frequency means phi equal HF naught. This is smaller means phi value will be smaller, that will have a value closer to the y-axis. So this will be, the work function also will be lowest. So remember, they all will be parallel to each other. So the emitting electrode with lowest threshold frequency will be more closer to the y-axis, and the work function will be also closer to the origin of the graph. Remember these things. Okay, so this is the definition of stopping voltage or stopping potential. Minimum voltage or minimum potential required to stop all the electrons, including the fastest electron, is defined as stopping voltage or stopping potential. Okay, so electron volt is a unit of energy. It's defined as the work done in moving an electron through potential difference of 1 volt is defined as 1 electron volt. Again, I'm saying the work done in moving an electron through a potential difference of 1 volt is defined as 1 electron volt. Okay, so that means W equal QV, we know that. We are moving an electron, so the charge of the electron is 1.6 into 10 to the power minus 19. We are moving it through 1 volt potential difference, so that is going to be 1.6 10 to the power minus 19 joule. This is defined as 1 electron volt. That's given in the data sheet. That means 1 electron volt equal 1.6 10 to the power minus 19 joule. Okay, so if you want to convert a joule to electron volt, say for example, find 2.8 into 10 to the power minus 20 joules in electron volt. If this is a question, how to convert, divide this value by this value. So energy is equal to 2.8 10 to the power minus 20 divided by 1.6 into 10 to the power minus 19 electron volt. Solve it, you will get the answer in electron 0.175 electron volt. Same way, to convert electron volt to joule, energy is equal to 2.4 electron volt. Find this energy in joules if they ask. So energy is equal to multiply by 1.6. So 2.4 electron volt means multiplied by 1.6 10 to the power minus 19 joules. So solve it, you will get the answer. So that's going to be 2.4 into 1.6 into 10 to the power minus 19. So that will be equal to 3.84 10 to the power minus 19 joules. So that's all theory related to photoelectric effect. We'll quickly summarize before doing few questions. So first you must know the failure of the wave theory to explain the photoelectric effects. I am not repeating it. I several times repeated during the start of this lesson. So again, watch it if you want. So that you must know the failure of the wave theory to explain photoelectric effect. Then when we start the equations, we know Max Planck proposed photons. So the energy of a photon is given by E equal hf, but F equals C over lambda. So it could be hc over lambda. H is the Planck constant given in the data sheet. Then we must know the minimum frequency required to remove an electron from the surface of metal is called threshold frequency. Minimum energy required to remove an electron from the surface of metal is called work function, that is given by hf naught or hc over lambda naught. So you know that C equal F lambda, so C equal F naught lambda naught, you must know that the relationship between threshold frequency, threshold wavelength, you must be able to define them also. Then in terms of intensity, we say the intensity of the electromagnetic radiation in terms of photon models given by I equal n times HF, where n is the number of photons passing through unit area per second. Then you must know the Einstein's photoelectric equation, HF equal phi plus Ke max HF or Hc over lambda. Anyway, you can write F equal C over lambda, I'm not writing it again. And phi equal work function, I told Ke max half mv max square. This equation is applicable only for surface electrons. Then we know the you must know what is stopping potential, minimum voltage required to stop all the electrons including the fastest electrons. So that is given by Ke max equal Q or E, charge of electron, into stopping voltage, you must know. Then by combining these two we can get an equation, and we plot graph also. HF equal phi plus QVS. Then you must know 1 electron volt equal 1.6 10 to minus 19 joules. So that's all you must know. Now we'll start, we'll discuss few questions related to photoelectric effect. Okay, so first question, threshold frequency of cesium metal is 5.16, 10 to the power 14 hertz. Light of frequency 6.2 into 10 to the power 14 hertz is irradiated, exposed on the metal. Find the work function of the cesium in electron volt. Work function, so we know the threshold frequency. Work function they are asking, we know the threshold frequency. So second equation I'm going to use for the first part. Work function phi is equal to HF naught 6.63 10 to the power minus 34 given in the data sheet. F naught 6.2, metal 5.16 is the threshold frequency. 5.16 10 to the power 14, this much of joules, you will get it in joules, that will be equal to 3.42 10 to the power minus 19 joules. But they ask you to find it in electron volt, divided by 1.6 10 to the power minus 19 to convert to electron volt. So when you solve, you will get 2.14 electron volt. Second part, find the speed of the fastest photoelectron. So second part, we have to use the equation HF equal phi plus half mv max square. Ke max means half mv max square. Mass of the electron is given in the data sheet. I didn't write this. That is 9.11 10 to the power minus 31 kilogram given in the data sheet. So don't worry about it. So energy of the photon, we need to find it, 6.63 10 to the power minus 34, that is the Planck constant. Frequency of the radiation is 6.2 10 to the power 14 equal. Work function, we found it in joules. So when we are using this equation, half mv max is there, so it must be all in joules. This must be joule. Work function, if they give it in electron volt, you have to convert to joule when you are using this equation. So work function given in joules, we found it 3.42 10 to the power minus 19 plus half mv max square. Half mass is 9.11 10 to the power minus 31, that's given in the data sheet, I didn't give it in the question, times v max square. Lot of numbers, carefully solve it. So we need to find the v max, solve it. You will get v max is equal to 3.89 10 to the power 5 meter per second. Third part, find the stopping potential for the fastest electron. So we know the kinetic energy K max is equal to QVS or EVS. K max we can calculate, we know the speed, so we can calculate the kinetic energy maximum, or we know the half into 9.11 10 to the power minus 31. We found the speed 3.89 10 to the power 5 all things squared equal Q is the charge of electron, which is 1.6 10 to the power minus 19 Vs. Solve it, you will get a stopping potential that will be equal to 0.43 volt. Okay, second question. Light of frequency 6 into 10 to the power 14 hertz incident on a metal surface emits photoelectrons with maximum kinetic energy of 2 into 10 to the power minus 19 joule. First part, calculate the minimum amount of energy needed to remove an electron, means that is the work function they are asking, first part. So HF equal 5 plus Ke max. So there we know the 6.63 10 to the power minus 34. Frequency is given 6 into 10 to the power 14 equal. Work function is the question. Fastest kinetic energy 2 into 10 to the power minus 19. Find the phi work function. So you will get electron volt. So this work function will be equal to they ask you to calculate the minimum amount of energy needed to remove an electron from the surface of metal. So solve it, you will get the work function, that is 1.978 10 to the power minus 19 joules. Second part, find the speed of the fastest electron. So second part, we know that we need to find the speed of the fastest electron. So we know the energy K max equal half mE max squared. Mass of the electron given in the data sheet. K max we know 2 into 10 to the power minus 19 equal half into 9.11 10 to the power minus 31 given in the data sheet. V max squared. Find the V max. That will be 6.63 10 to the power 5 meter per second. Okay, so third part, find the stopping potential. So already we found the kinetic energy of the fastest electron. We found this. We know the kinetic energy 2 into -10. Stopping potential they are asking. So third part, we know that QVS is equal to Ke max. 1.6 10 to the power minus 19 is the charge of electron. Vs equal kinetic energy 2 into 10 to the power minus 19. Find the Vs. So Vs will be equal to 1.25 volt. Fourth part, what will happen to the stopping potential when the intensity of the radiation is increased without changing frequency? So no change in frequency. So we know that. So fourth part we say, since no change in frequency, HF equal 5 plus Ke max, then no change in Ke max. F is constant, phi is constant, so then Ke max is also constant. Then you should say therefore QVS also constant, because K max equal QVS, no change in Vs. Stopping potential will be the same even when you increase the intensity by keeping the frequency constant. Okay, third question. First part, a metal is irradiated with same intensity of red light and blue light separately. And both the photocurrents and stopping potentials also measured. They are measured separately, having separate experiment. Compare the photocurrent when the blue light and red light were irradiated separately. Both have the same intensity. Okay. Photocurrent. Photocurrent means rate of flow of photoelectrons. Higher the number of photoelectrons, greater the photocurrent. Both blue color and red color lights were irradiated on the metal separately during each experiment. Both the photocurrent and stopping potentials were measured separately. Now we should know they have the same intensity, means intensity of blue is equal to intensity of red for the light. I equal n times HF. So number of blue photons falling on unit area per second into HFB is equal to number of red photons falling on unit area per second times HFR. Both have the same intensity, so that's the reason I equate the intensity of blue to intensity of red. Intensity of blue is given by according to the meaning of intensity in terms of photon model, number of blue photons falling on the metal per unit area per second into H into Fp. This is the energy of photon of blue color. This is the energy of photon of red color into number of red photons falling on unit area per second. H and H will get cancelled. Now Nb Fb is equal to Nr Fr. Okay, we know the frequency of blue is greater than frequency of red. We know that x1, y1 equal to x2, y2. And if I say y1 greater than y2, then x1 should be less than x2. Simple mathematics. So according to that, if we use the same idea, we know frequency of blue is greater than frequency of red with GR. So since Fb greater than Fr, we can say Nb less than Nr. The number of blue photons falling on the metal per unit area per second is less than number of red photons falling on unit area per second. Then we should say one photon removes or interacts with only one electron. One photon only one photon knocks out, better say knocks out only one electron. Then you should say, since the number of red photons greater than blue photons, more number of electrons will be released by red color photons. Since Nr greater than Nb, more number of photoelectrons will be released per second or removed or will be released per second by red color light. So more number of photons are released by red color light, means rate of flow of electrons will be more for red color light. Hence there will be more rate of flow of electrons rate of flow of photoelectrons when red light is irradiated. So finally you can give the conclusion. Photocurrent will be more when red light is irradiated. Photocurrent will be more because rate of flow of photoelectron is more because red color photons are more number of red color photons are falling on unit area per second. So the photocurrent due to red color light will be more than blue color light. Okay, second, but compare the magnitude of the stopping potential. Stopping potentials also measured separately when blue light and red light were irradiated on the metal. So we compare the stopping potentials separately. Blue color light has greater frequency. So according to HF equal 5 plus KE max. Since blue color light has greater frequency, than red light, KE max will be greater for blue color light. So then you can say KE max equal QVS. Then you can write the conclusion. I am not writing. So for blue color light, KE max greater means stopping potential will be more for blue color light. That you should give the final conclusion. Okay, fourth question. A student shines light from UV lamp onto a metal surface. Calculate the maximum kinetic energy in joules. Photocurrent joules of the photoelectrons. Frequency of the UV given. Work function of the metal is given, but it's in electron volt. A simple question, but I put this question because the electron volt work function is given. Electron volt must be converted to joules. Students make mistake normally. Otherwise, it's nothing. This simple question. So the frequency given HF equal 5 plus KE max. Frequency is given 4.2, so 6.63 10 to the power minus 34, that is H. Frequency is 4.2 into 10 to the power 15 equal work function given in electron volt. Careful, when you are using KE max, it must be in half MV max. If they ask you to find the kinetic energy in joule, you have to convert this to joule. So 4.1 into 1.6 10 to the power minus 19. Conversion of electron volt to joule is multiplied by 1.6 10 to the minus 19 plus KE max. Solve it, you will get the KE max in joules. So that you will get answer KE max will be equal to 2.13 10 to the power minus 18 joules. Okay, second part of the same question, student replace. Actually, it's a past paper question. They put teacher, I think. I just wrote it on a paper. A student replaces the UV lamp with a more powerful source which emits UV radiation of the same frequency. Explain why this results in more photoelectrons being emitted per second. Okay, same intensity. So they are saying it's a more powerful source means higher intensity. So more powerful source means greater intensity, but it's explained same frequency. So we know that intensity is the same, but even we call UV radiation, you can have different intensities. So we know that intensity is given by I equal N times HF. So the intensity is higher because more powerful means higher intensity. Same frequency, they are saying same frequency. So N is increasing, I increases, N is increasing. That means it's emitting more number of photons per unit area per second. One photon removes one electron, so more electrons will be released per second. That's the reason more electrons being emitted per second. Here I wrote more powerful source means greater intensity. I equal n times HF. I didn't define what is n. In the exam you must define what is n, number of photons per unit area per second, because this is not a standard equation. So you must define what is n. I didn't write it. Anyway, since I explained already, I didn't write it. But in the exam, when you are using this, you must define what is n. So n increases, one photon knocks out or interacts with only one electron, that you must say, because that's one of the postulate proposed by Albert Einstein. So that you must say that. This is an Edexcel IAL past paper question. I can't remember the year. I didn't write the whole question. The diagram was given, and they are saying the gold leaf electroscope is a device that can be used to detect charge. You had it in IGCSE. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. In the demonstration of photoelectric effect, the teacher charged zinc plate with a negative charge. So it's charged to negative. So the central rod or central stem and the gold leaf, they carry negative charge. So there is a deflection. The amount of deflection depends on the concentration of charge. Higher the charge, greater the deflection. When the amount of charge is reduced, the deflection will decrease. You had it in IGCSE, that one. The question is, when the ultraviolet radiation of 2 into 10 to the power 15 Hertz was shown on the zinc plate, the deflection of the gold leaf reduced. So when it is irradiated with a UV radiation, the gold leaf moved down. The question is, explain why the deflection of the gold leaf reduced. Your answer should include a calculation, 4-mark question. Okay, so the work function of the zinc also given 6.9 10 to the power minus 19. Simple, only thing we need to find the energy of the photon of UV radiation, and we should show energy of photon of UV is greater than work function. Then you should say one photon interacts with one electron of the zinc plate, and electrons are removed from the zinc plate. When the zinc plate loses electron, it attracts the electron from the gold leaf and the central stem. So the concentration of the charge decreases. So the deflection decreases. Nothing. So only thing 4 marks, but simply you can get. We'll do the calculation first. So for the zinc plate we are going to write. So for the zinc plate, HF is equal to, we'll find the energy of the UV radiation, we'll find the energy of the UV radiation 6.63 10 to the power minus 34, and the frequency 2 into 10 to the power 15. So you solve it, you will get 1.326 10 to the power minus 18 joules. But this is 6.9 10 to the power minus 9. If you want to put this in 18 10 to the power minus 19, you can write this here 13.26 into 10 to the power minus 19 joule is the energy of the UV photon, that is greater than work function of zinc. So the energy of the photon is greater than work function of the zinc, because that is 6.9 10 to the power minus 19 joules. Then you should say, since the HF greater than 5, one photon will interact with one electron of the zinc, and zinc will lose electrons. You can continue, I am not writing. When the zinc loses electron, it will become positively charged. It will attract electrons from the gold leaf and central stem. So the concentration of charge will decrease, deflection will decrease. That's the answer. Okay, the same question, second part, the past paper question. Explain what would be observed with the gold leaf electroscope if ultraviolet radiation of the same frequency but with a lower intensity was used. It's a 4-mark question. So same intensity with the ultraviolet with the same frequency, lower intensity, same frequency but lower intensity, what would be observed? Nothing. We had used same thing again, same intensity. So you should say same intensity means I equal n times HF. You should define what is n. I am not writing, but you must write in the exam. So lower intensity means same frequency, lower intensity means number of photons falling on the zinc plate per unit area per second will be lower, is it? Lower intensity, same frequency means n will less. You should define what is n. Number of photons falling on zinc plate per unit area per second will be lower. Then you should say one photon interacts with one electron, and hence the number of electrons released per second will be lower when the intensity is lower. Therefore, it will take longer time for the gold leaf to become vertical. That's the answer you should say. I'm not writing, you can understand it. Okay, so this also past paper question, but you know that already I explained. Explain how the existence of a threshold frequency supports the particle theory of light and not the wave theory of light. Okay, first you should say what's the failure of wave theory. According to wave theory of light, any frequency of radiation should be able to remove electron from the metal, but it was not observed. Then you should say, according to particle theory of light, to remove an electron, the energy of the photon, which is given by HF, must be greater than or equal to a minimum amount of energy required to remove the electron from surface of metal called work function. So the energy of the photon must be greater than or equal to work function. Work function is given by HF naught. Therefore, HF must be greater than or equal to HF naught. F must be greater than or equal to F naught, and you should say one photon interacts with one electron. Therefore, to remove an electron, the frequency of the photon must be greater than or equal to minimum amount of frequency required to remove the electron from the surface, which is called threshold frequency. That's the answer you should give. So this is the answer for 4 marks. I already explained these things. You can say here if not is the threshold frequency. Okay, so I hope that's the end of this photoelectric effect. I hope you understood all. I think it's useful to you. Okay, so we'll meet during the next lesson. Bye.